Right, welcome to the P2 exam revision live stream. Hopefully we're live now and you're watching us, or you're watching this back maybe on Thursday night or during Thursday. Either way, you're going to get all this good information about the P2 exam and hopefully get you through that last exam that's on Friday just before you can enjoy your 12-week break that you've got coming up and do something really good during that time. I do mean it with all sincerity when I say that you've earned the break. Okay, you've worked really hard, and it's good if you are watching this that you've really engaged with it up until the last point, because this exam still is 25% of your overall additional science GCSE. It's a large chunk, and I know you've been putting in the work up until this point, so it'd be a shame for that to get lost if we don't do as well in this P2 exam. So really, this is the last big one, and hopefully this stream will help you through it. If you do have any questions while we're live, email at communications@folkestoneacademy.com. All the comments should be active, so you can comment on the video. If it's a big question, I'll answer it in the PowerPoint for everyone. But if it's a smaller question, we might just type back and answer some of your questions that have been coming in, just the little bits that we can just pick up for you. Just going to start my timer as always, so I know how far we've got through. Obviously we've got an hour and a half to get through as much as we can. I'm going to cover some of the main points in a bit more detail, and then go through some of the other bits in just brief detail. I won't get time to cover everything in P2, but as I say, by looking at the papers I can sort of make a little bit of a prediction in what's going to come up, or what I think is going to come up, and cover those main points. And hopefully cover the things that will come up in the exam on Friday morning. I will also be in on Friday morning from about 7 o'clock, just to give you that last minute help you might need, just for any questions you might have, just to really refresh those things in your head. If you've got a question you want to ask that's come up in your revision, or you just want that little boost, that little reminder, that little refresher at the last minute. Right. So, getting into it, okay, starting with P2. The first topic in P2 you probably did at the end of year 10 was all to do with speed and velocity. So, speed and velocity. They are slightly different. They are slightly different things. My screen's gone a bit blue again. There we go. Hopefully sort that out. They're slightly different things. Speed is just how fast an object is travelling. So, speed has nothing to do with its direction. It's just how fast an object is moving. Okay, it's measured in science in meters per second is the speed, whereas the velocity of an object is slightly different. The velocity of an object is actually the speed the object is moving in a certain direction. Okay, so that's what the velocity is. That means that an object can change velocity if it changes its direction, even if it's moving at a constant speed. So when a car goes around a corner, even if it stays travelling at 30 miles per hour, it's still changing its velocity because it's changing the direction it is travelling in. So that's the difference between velocity and speed. Velocity includes a direction. It's actually called a vector, so velocity is a vector. And it's slightly different to the vectors you might come across in maths, but velocity is a vector because it has not only a size, how fast, but also what direction it's moving in. Now, there's a calculation you can do to work out the speed or velocity of an object, and that is speed is equal to the distance divided by the time. Okay? So if you know how far an object travels in a set period of time, then you can work out its speed. It's very important though that you get the units correct here. Distance needs to be measured in meters, and in exam questions they are not adverse, they're not against giving you a question where the distance is in kilometres. You need to remember that there are 1,000 metres in a kilometre. So if you've got 3 kilometres, you need to recognise that that is 3,000 metres. You need to convert it to metres. Similarly, time needs to be measured in seconds. So time needs to be in seconds. If they give you a time in minutes, 2 minutes for example, you need to convert that by timesing it by 60, because there are 60 seconds in a minute, to get the units correct, to get it into seconds. So 2 times 60 would be 120. There are 120 seconds in there. So if we converted that to 3,000 metres, divided by 120, our speed would be worked out in metres per second. Okay? If you are the sort of person who likes a triangle, now some people don't like these triangles, they don't think it's doing it properly, but you may be asked to work out other things, not just the speed. You could be asked to calculate the distance or the time given the other two quantities. To do that, if you want to use one of these triangles, if you can't rearrange this equation, then you will need to cover up the thing you want to work out. So for speed, just like here, if I covered it up, it is distance over, so divided by time. That's how I calculate the speed. But if I wanted to work out the distance, if I covered that up, it would be speed multiplied by time. And if I wanted to work out the time, if I covered up the time, it would be distance divided by speed. Okay, so I can use the triangle. This, like calculation, speed is distance divided by time, is one that's, funnily enough, not actually found on your formula sheet you'll be given. In the exam, you'll get a formula sheet just like this one, with lots of formulas on it this time. It's double-sided. And there are the formulas you'll be given. Count yourself lucky, because Year 10 don't have a formula sheet that's anywhere near as detailed as this. They have to remember lots of these, but you get this, so do use it. But this one, speed is distance divided by time, is not actually found on this. I'll refer to this when we talk about some of the formulae that do come up in the exam in other places. So you can calculate the speed of an object in metres per second by doing the distance in metres divided by the time it takes. Those are the simple things. Those are usually the first sort of calculations you do on speed or talking about speed. It then goes on to what's called a distance time graph. A distance time graph is a graph that will look like this, where you've got distance along your y-axis, along the side of the graph, and time along the bottom. The time hopefully will be in seconds, and the distance will be in metres. Okay? And from that you can work out a few things. Concentrating first of all on this sort of red line here, this shows the motion of an object. When the line is going up and the line is straight, that means an object is moving at a steady speed in a distance time graph. And you could find that speed by doing the distance it had travelled, reading it off the graph, and dividing it by the time it took to reach that distance. If the line is flat on a distance time graph, that means the distance is not increasing, i.e. the object is stationary, the object has stopped moving in a distance time graph. Okay? And then when the line goes down, it means that object is returning to where it started from. It's still moving, because this is distance 0 from a point, and it's returning back to that point. So it's actually moving at a steady speed back towards where it started from. What we can also tell from this is the steeper the line. So this line in green here is actually a steeper line than the line in red. That means that object is moving at a steady speed, because it is a straight line, but it's faster than the red line. So the steeper the line, the faster the object is moving. Okay? But if it is a straight line, it is a steady speed or constant speed. If you have a curved line like this in a distance time graph, like the line in blue, that means the object is actually accelerating. It is changing its speed. It's not a constant speed. Okay? But you wouldn't really be expected from this graph to work out the acceleration, but you could from the next graph we're going to look at in a second. Okay? So key points: if the line is straight, it is a steady speed or constant speed. If the line is horizontal, it is stationary or not moving. When the line goes back down, it is actually moving. It's not getting slower, it is returning to where it started from at a steady speed. Okay, they're the important bits. And as I say, you can calculate the speed by working out the gradient of the line, or the steepness or the slope of the line. So you would work out how far the object travelled in how long it took to do that. Okay? So that's how you work out the speed from a distance time graph. Now this is slightly different to the other type of graph we need to look at. The other type of graph is called a velocity time graph. Okay? It's different because it doesn't have distance along the y-axis, along the side. It actually has velocity, or speed, if you want to think of it like that, okay, in meters per second. And it still has time along the x-axis, along the bottom. So now this is actually velocity along here, or speed along the y-axis. So it makes a difference to what these lines are showing. In this, if you have a straight line, it is constant acceleration, not constant speed or velocity, it's constant acceleration, okay, if the line is straight and going up. If the line is horizontal, that does not mean the object has stopped moving in this case. It means it's at constant velocity. And in fact, you probably can't see the numbers, but I can read it off here. It's a constant velocity or constant speed of 8 meters per second. Okay, it's not stationary, it's just not accelerating anymore. Its speed is remaining constant. The only way you could show the object being stationary on a velocity time graph would be if the line was horizontal along the bottom axis, because this is a velocity of 0. So this would mean the object was stationary if it was horizontal here. But if it's horizontal anywhere off the bottom axis, then it's moving at a constant speed, and the speed or velocity can be read off of the graph. When the line returns down, in this case, it's actually decelerating, or you can call that negative acceleration. It's moving downwards, the line, so it's decelerating. It's going from this velocity down to, in this case, 0. So it's decelerating. The gradient of the line, or how steep the slope is, tells us how fast it's accelerating in a velocity time graph. The steeper the line, the quicker the object is accelerating, or the faster it is accelerating. And you can actually calculate the acceleration using that line. Because acceleration is change in velocity, so it's how much it's changing. Now if it starts from the bottom, it's quite easy, because it starts at 0 and it goes up to 8 meters per second. And then the time it took to do that is 4 seconds. So I can do, to work out acceleration, which is one of the formula on your graph, it's change in velocity. You do the final velocity, which in this case is 8, subtract the initial velocity, which is where it started, 0, and you divide it by the time it took to do that, 4 seconds. So 8 divided by 4 tells me it is accelerated at 2 meters per second squared. That's the units for acceleration. I'll put it up again a bit later, but the units for acceleration are meters per second squared, which are funny units. They're weird units for acceleration, but that's what it is. We'll show that again a bit later. So you can calculate the acceleration from the slope. And last of all, and this is the tricky bit with a velocity time graph, you can calculate the distance the object has travelled. But to do that, you actually have to find the area underneath the line. Okay? And to do that, you need to be able to do areas, like in maths. You need to divide your area underneath the line into sections. This first section here is going to be a triangle. Okay? And to work out the area of a triangle, it's half the base times the height. Okay, to work out the area of the triangle that's under this portion of the line here. The bit where it's at constant velocity, that's actually a rectangle, so it's really easy to work out the area under that because it's just the base times the height to get the area of a rectangle. And similarly, when we get to the last section, again it's a triangle, so it's half the base times the height to get the area under this last section. If we wanted to work out the distance, the total distance travelled, we would have to add those 3 areas together to get the total area under this whole section. But what you need to watch out for in exams is they often ask you for the distance travelled in a specific part of the journey. Now for this one it could be, work out the distance travelled when the object was moving at a constant velocity. That could only be this section, or would only be this section just here. They could ask you a different question. The question could be, work out the distance travelled when the object was decelerating. That you would have to realise is only the area under this section here, because this is when the object is decelerating. So you'd work out that area and it would tell you the distance travelled. Or the last one could be, for a graph like this, work out the distance travelled when the object is accelerating. And that would be the area when the line is going up. Okay? So those are things they can ask you about velocity time graphs. Remember, velocity time graphs and distance time graphs are different things. In a distance time graph, if the line is straight and going up, it's moving at a steady speed or constant speed. When it's horizontal, it's stationary. And when it's moving down, it's moving at a steady speed but returning to where it started from. In a velocity time graph, it's different. When the line is going up, it means constant acceleration. When the line is horizontal, it means constant velocity or constant speed. And when the line's going down, it's constant deceleration. Okay? The steeper the line, the faster the acceleration on a velocity time graph. Okay? So what causes objects to change their motion, to change their speed, to accelerate, if you like? It's all to do with forces. Now I appreciate some of the wording on this probably that you're looking at is quite small. You can obviously find the PowerPoint on our science website if you haven't done that already. First thing I'm going to say about forces is the units for forces. The units for a force is always newtons, or just given the letter N. That's named after Isaac Newton, who was the person who discovered gravity, or put a name to gravity really. So newtons are the units for force. So if you ever get a question asking you about forces, the units for a force must be in newtons. It's also how you could identify you've got a force. If it says something newtons, you know that they're talking about a force of some kind. You need to be able to identify different forces on an object. So if you've got an object, you want to identify the forces that are acting on it. Most forces are either a push or a pull force. If I've got a object just such as a block on a table, sitting on a table, there are going to be forces acting on that object even when it's stationary. A force that's always acting on an object when it's on Earth or on the planet is a force pulling it down. Now, that's actually going to be gravity that's pulling, and gravity acts towards the centre of the Earth. It pulls down towards the centre of the Earth. Now that block is not falling through the table, it's not falling down. So if there's no change in motion, which there isn't in this block that's on a table, there must be an equal and opposite force acted on it. And that must be moving in the opposite direction, upwards. That, if you're pushing against an object, so when I'm pushing against the desk, okay, there's an equal and opposite force pushing me back. That's why there's no change in motion. There is no acceleration. Okay? So that is called the reactive force because it's pushing back on the table that it's resting on. Okay? So that's a force diagram where I've just labelled up some of the forces. If it was an object moving, you could label some more forces on that. There may be a push force moving it forward, which you could label up, or you can say if an object's moving directly up, like a rocket, that would be thrust. If an object's floating in water, you can say up thrust is acting on it. A force that acts against an object's motion, you can call drag forces, but if an object's moving through the air, it will be experiencing air resistance, and we'll come to air resistance when we talk about falling in a bit more detail. Okay? So this object is resting at rest on a desk, this block, so gravity is pulling it down, but it's not falling or accelerating downwards, so therefore there must be an equal and opposite force exerted back, which is balancing the gravity pulling it down. Okay? So there is no change in motion for this block. Now, something you've got to be really clear in. When I say no change in motion, that can mean two things. Okay? There is no change in motion if an object is stationary. Okay? Me now, I have no change in my motion. But there is also no change in motion if I am moving at a constant speed. Okay? As long as I'm moving at a constant speed in one direction, that means there is no change in my motion. So forces are balanced. Okay? It can mean one of two things. Constant speed, well really it only means constant speed. When an object is stationary, it has a constant speed, but that constant speed is just zero. Okay? So if forces are balanced, there will be no change in motion, or the object will move at a constant speed, which could be zero, meaning stationary. Okay? In this tug of war, these two people are pulling the rope. They're exerting equal forces in opposite directions, so they balance out. They're balancing each other out, and there is no change in motion. The rope is not moving. Okay? If there is unbalanced forces, what we call that is we say there's a resultant force acting on the object. So when forces are unbalanced, we say there is a resultant force. And when forces are unbalanced, it means the object must be accelerating. So when forces are unbalanced, it leads to acceleration. In this example here, we've got a lorry moving forward. There is a force pushing it forward of 100 newtons. So I'm going to simplify that diagram somewhat because my drawing is rubbish, as anyone who's been in my class knows. So this is my lorry. Beautiful, okay? And in this case, if I had a force pushing forwards of 100 newtons, there would be a force acting in the opposite direction. This would be drag, or could be air resistance. And this is actually acting with a force of 60 newtons. Okay. Now, I can work out what the resultant force would be and in which direction. So resultant force in this situation would be the force to the right, which is 100 newtons, subtract the force to the left, 60 newtons. Generally, we always put the bigger force, we subtract the smaller force from the bigger force, and that leaves us, in this case, with a resultant force of 40 newtons. Now, I could be asked to show the direction of that resultant force, or I could be asked to describe it. It would be 40 newtons to the right in that diagram. Now, to show it by an arrow, the resultant force would be in that direction, resultant force of 40 newtons. Okay? So I could show it on the diagram. Sometimes you can be asked to do that. The resultant force, because this object, this lorry, has a resultant force acting on it, it means there will be a change in motion because forces are unbalanced. And the change in motion means that this object will be accelerating. Okay? Remember, if forces are balanced, there is no change in motion, the object moves at constant speed. If forces are unbalanced, the object is accelerating in the direction of the resultant force that's acting on it. Okay? And we can do something with that force. We can actually use that force to do a calculation on the actual change in motion of that object. And that leads to a really important calculation you can do, which is actually the force in newtons is equal to the mass in kilograms of the object multiplied by the acceleration. Now, if I was to know the mass in kilograms of this truck, I could actually rearrange. So I'm going to say it's 100 kilograms, the truck, which is much less than it would be in reality, but we're going to use that for now. Now I know the force in the direction, and I know the mass of the object. I can actually rearrange this. And force equals mass times acceleration is one of the formulae you're given, and they even give you it two ways. They give you it so you can work out the acceleration. Acceleration is equal to force divided by the mass. Okay? So if I was to do that for this, acceleration, let's go with a lovely green. Acceleration is force divided by the mass. In my case, my force I worked out to be 40 newtons. And my mass, I said, was 100 newtons. Okay, my acceleration is equal to 0.4 meters per second squared. Okay, meters per second squared is the units for acceleration. Meters per second squared, a bit of a weird one, but that's the units for acceleration. So, I can work out the resultant force acting on an object. I know what happens if forces are balanced, there's no change in motion. I know what happens if forces are unbalanced. There is a change in motion in the direction of the resultant force, and that change in motion means acceleration, or the object is accelerating. Okay? Now, when we go back to my original example, the block just on the table, I said gravity is pulling it down. Gravity is a downwards force, and it results actually in weight. An object has a weight due to gravity. And something you've got to be clear with in P2 is that weight and mass are different things. Okay, they're not the same thing. Even though people go, how much do you weigh? Oh, I weigh about 94 kilograms. Okay, that's not strictly true, because weight is a downwards force. And I said earlier that all forces should be measured in newtons. Okay, so it's incorrect. People should say, what is your mass? And the definition of mass is how much matter an object is made from. So the amount of matter that makes up an object. Mass is always measured in kilograms. Okay, the units for mass is kilograms. Whereas weight is a downwards force, and it depends on gravity as to how strong it is. So I can actually calculate the weight of an object based on its mass and the gravity. Now, gravity on Earth is always the same. You will be given it, but gravity on Earth is 10 newtons for every kilogram of mass. If I was to use this example as an example, I could say my block weighed 10 kilograms. And this is on Earth, so the gravity on Earth, the gravitational pull on Earth is 10 newtons per kilogram. So to calculate the weight of that object, the weight of that block, all I have to do is the mass multiplied by the gravity. In my case, my example, the weight is going to be equal to the mass, which is 10, multiplied by the gravity, which is 10, which equals 100 newtons. Okay? So that's how you can calculate the weight of an object. You need to know its mass in kilograms, and the gravity, which if it's on Earth will always be 10, but you should be given in the question anyway. So gravity pull it down to calculate the weight of an object. Okay? The mass is measured in kilograms, it's how much matter an object is made up from. The weight is a downwards force and is measured in newtons. That leads to this. This is to do with an object falling through the air or falling through a fluid. A fluid could be a liquid, but in most cases they use air as the object, the medium that the object is falling from. When that object is falling, it's actually experiencing, well, two forces really, two main forces, and those forces change dependent on things. Okay? The maximum speed an object can reach when it's falling is called the terminal velocity, and the terminal velocity depends really on the air resistance of the object. They could ask you about the fact that if you drop two objects in a vacuum where there is no air, they will accelerate at exactly the same speed. So if I was to drop a bowling ball and a feather in a vacuum, they would actually fall at the same speed and hit the ground at exactly the same time. The difference if you drop them outside of a vacuum is the absence of air, when you've sucked all the air out of a room, or there's no particles whatsoever. If I was to drop them in this room, a bowling ball and a feather, the bowling ball would hit the ground first, because air resistance would slow the feather down when it's descent. Okay. The maximum speed an object can reach when it's falling is called its terminal velocity. Okay. And a good example of this is a skydiver. If you've ever done skydiving, you'll experience terminal velocity at a point where you can no longer accelerate. You cannot get any faster. Okay? When the skydiver first jumps out of the plane, that is scenario A here. The only force that's really acting on them is their weight, and their weight is acting downwards towards the centre of the Earth. Okay? So weight is acting downwards on the skydiver. So at A, when the skydiver first leaves the plane, the only force acting is weight or gravity pulling them down. This means that the forces are unbalanced. So forces are unbalanced. The object, or the skydiver, accelerates. Now, they're accelerating rapidly at first because the resultant force is large, because the only force acting on them is weight. There is no air resistance at this point. A few seconds after they've been falling, we reach scenario B, where the drag force, or the air resistance, has begun to increase. The amount of drag, or air resistance, an object experiences is proportional to the speed that it's travelling. It's related to the speed. The faster an object moves, the greater the air resistance. If this skydiver wanted to increase his speed, what could he actually do? He could make himself more streamlined, and that would lower the force of drag and therefore give a bigger resultant force and mean he would accelerate. So that's what streamlining is all about. You're lowering the force of drag and therefore unbalancing the forces and causing acceleration. But let's go back to this scenario. So we are at B, a few seconds after the skydiver has jumped out of the plane. In B, the force of drag or air resistance begins to increase. Oh, can't spell today. Okay. But it's still smaller than the weight. Let's say as the object speeds up. Okay, so it's still smaller than weight. This means forces are still unbalanced. And therefore the skydiver still accelerates. They've not reached terminal velocity at that point, okay, because forces are still unbalanced, there is still an acceleration, okay, so that's at B. Finally, we get to a situation, as they get faster, the force of drag increases, until we get to situation C. Situation C is terminal velocity, okay, it's the fastest that person can move in, unless they streamline themselves to reduce drag, but we're going to assume they don't do that. So this is their terminal velocity, the fastest they can fall. And at point C, what has happened is the force of drag has become equal to air resistance. Drag has become equal to, weight, or gravity, okay, because drag and air resistance is the same thing. So the force of drag has become equal to the weight. The forces are balanced, or forces are now balanced. Therefore, no more acceleration. That does not mean that the person is stopped in mid-air, forces are balanced, but clearly he's not stationary. He's still going to fall, but he won't get any faster. He's at terminal velocity. I'm not going to go through the exact scenario, but you can have a think about what would happen if he opened his parachute at that point. So he's reached the maximum speed he can fall, he's at terminal velocity. If he opens his parachute, is that going to change his weight, pulling him down? No, it won't. Your weight will not change. So this force will stay the same. But he will increase his drag massively by opening up the parachute with a large surface area. Will increase his drag. That means forces will now become unbalanced again. It doesn't mean he moves up. If you've watched a video of a skydiver, when they open their parachute, they don't shoot upwards. It looks like that because the cameraman is still falling, but they've actually just decelerated. They've slowed down. Because the forces are unbalanced, means there's a change in motion because drags become much bigger than weight, resultant force is upwards, so they decelerate upwards. Eventually, as they slow down, the force of drag goes down because the slower you are, the less drag becomes, and they will reach a new terminal velocity, which is less than the first. Okay? So that's what happens with an object falling, and skydiving is a thing that occasionally comes up, or someone jumping out of a plane, or an object falling through the air, and those are the stages that are in it. Initially, the only force pulling it down is gravity, so it's accelerating rapidly. The faster it falls, the more drag increases, but forces are still unbalanced to this point, so it will continue to accelerate downwards. At this point, shortly after the skydiver has jumped, the force of drag is equal to the weight, and therefore the object has stopped accelerating. It's moving at a constant speed because forces are balanced. So that's forces, and now we're going to jump a bit onto electricity and charge. Okay, the first thing we're going to talk about is we're going to talk about how we charge up an object. And I'm sure all of you have experienced this. I get it often here when I walk down the corridors. I probably drag my feet along the ground because when I touch the railings, I get a static shock. And that's because static electricity is built up in me or on me, and it's discharged when I touch the metal railings. Okay? The way it's built up is you build up charge on an object by rubbing the object with an insulator. The objects have to be insulators. An insulator means an object that does not conduct. So you couldn't use a metal to do it. You couldn't charge up a metal rod this way, but you could charge a plastic pen or a plastic rod by rubbing it with a cloth, which is also an insulator. It does not conduct electricity. And what happens is, you do need to know atomic structure for physics, but I'm not going to go through it. I went through it at the start of my chemistry stream, so if you're still not sure of atomic structure, go back and look at the first bit of that. But we should know by now, electrons are on the outer shell or outside the nucleus of an atom. And electrons can be knocked off of atoms. So when you rub an object with a cloth, you can actually knock electrons off of it. When you knock them off of the rod actually becomes positively charged because it's lost electrons. And when it becomes positively charged, because you've knocked electrons off the surface, it's charged up with electricity. Okay? And similarly, if you rub it with an object and the electrons get knocked off of the cloth and go onto the rod, so it gains electrons, the material gains electrons, it will become negatively charged. If you put two objects which are negatively charged next to each other, like charges repel, so they push away. So it's why if you rub a balloon on your head, you actually charge up your hair, and your hair all gets negatively charged. That makes your hair stand on end because the opposite charges in your hair are repelling each other and pushing away, and your hair actually stands up. Similarly, your hair is attracted to the balloon because your hair has become negatively charged and the balloon positively charged, and opposite charges actually attract. So that's why opposite charges attract, your hair is attracted to the balloon, but your hair stands up on end because like charges repel, they push away from each other. Okay? So you can charge an object, and charge is it having electrons, gaining electrons, by rubbing it together. Now in electrical circuits you can actually calculate the amount of charge on an object, and charge is given the symbol Q, and it's actually measured in coulombs is the units. is equal to I, which I, funnily enough, is the current multiplied by the time. This is one of the formulas you have on your formula sheets. You don't need to remember it, and it does tell you what these things mean. So it tells you that I is the current, Q is the charge, and T is the time. So do remember you've got this sheet, and if you're not sure of something, you can refer to it to work out what's on it. Okay? So you can charge an object by rubbing it with an insulator, or charge an insulated object by rubbing it with another insulator. If you knock electrons off the surface, it will become positively charged. If you knock electrons off the cloth onto the object, it will become negatively charged. And the reason those electrons are important is electrons are what actually flows around a circuit when electricity flows. Electrons are what actually carry the energy around the circuit. Electrons are present in, well, free electrons are present in metals. So usually in a circuit, the wires are made of copper, and copper is a metal, and when we did C2 we talked about the fact that metals have free electrons. It's why they conduct electricity. And the current of an electrical circuit is actually the flow of electrons around that circuit. And the current is measured in amps. So we can measure it using an ammeter, and it measures the amps that is actually the flow of electrons, the current around that circuit. And they'll be flowing around the wires, and you'll be able to measure how fast they're flowing. Then you've got potential difference. The potential difference in an electrical circuit is the amount of energy carried by the electrons. And it's actually measured in volts, V, and can be measured in a voltmeter. Now these circuit symbols that are behind me on the board, you need to know these ones for GCSE, all of them, unfortunately. Some of the main ones you probably recognise, like a cell or a battery. Your lamp, there's two symbols for a lamp actually. This is one with a big cross in it, or big X in the middle of a circle, but there's another one as well you could use. Voltmeters and ammeters. Resistors are a tougher one to know, but they're just a rectangle in the middle of two wires. You have a variable resistor, which is that same rectangle between two wires, usually with an arrow on it, it could be a line. A thermistor. Now a thermistor is a type of resistor, and resistors resist the flow of electricity. A thermistor changes its resistance to electricity dependent on, therm means temperature. So depending on its temperature, it can change its resistance. If it is hot, it can have a low resistance. If it's cold, it can have a high resistance. Then you also get an LDR, which is a light-dependent resistor. Light-dependent resistors change the amount of resistance they apply to the circuit, dependent on the amount of light they receive. These are used in things like solar lights. So when a solar light picks up light, the resistance changes, and they can light up at night when it gets dark. Other tricky ones are diodes, which only allow electricity to flow through in one direction, and LEDs, which are lights that only let electricity flow through in one direction, but give out light when they do. Okay? But these circuit symbols are the circuit symbols you need to know. So if you get my slides, they're the ones you'll need to know for GCSE. So I talked about current being the flow of electrons around a circuit, and potential difference being the energy carried by those electrons. The resistance, I mentioned it, of a circuit is how difficult it is for electric current, electrons, to flow through an object. If an object has high resistance, it's difficult for electricity to flow through that object. If it has low resistance, it's easy for electrons to flow. I think of it like a doorway. The resistance is how many people can fit through the doorway. Okay? At the moment, a standard door, you could probably fit 2 people through the doorway. That's its resistance. If you made the doorway wider, you could fit more people through the doorway. There you've actually lowered the resistance. And if you made the doorway smaller, less people could fit through the doorway. You've actually increased the resistance. It's important to know that resistance is measured in ohms, and the unit, or the symbol, sorry, I should say, for ohms, excuse me, is this. Okay? It's actually a Greek like omega, but that's the symbol for the units for ohms, which is resistance. It's measured in ohms. And the resistance of a wire, so if we're talking about a wire which do resist electricity, depends on two things. The length of the wire. If you increase the length of a wire, you will increase its resistance. But also the thickness of the wire. Now, like my doorway analogy, if you're trying to squeeze through a very thin wire, that's going to be hard, so a high resistance. Whereas if you have a wide wire, it's going to have a lower resistance. Electricity can flow through easier. So you can change resistance in a wire by changing its length or by changing its thickness. You can actually calculate the resistance of a wire using this formula, which again is another one on your formula sheet. V equals IR. The things in this, V is the voltage or the potential difference of the circuit you're talking about. I is still the current, so I is the flow of electrons through that, the current in amps, and R is the resistance. Okay, so you can calculate the resistance of a circuit using that formula, but it is on your formula sheet if you need to work it out. When we talk about resistance, there was a guy called Ohm who came up with this idea that the current flowing through a resistor at constant temperature, must be at constant temperature, is proportional to the voltage across the resistor. Okay? That led to a graph that looked like this. Okay? It's a straight line. That tells me it's a constant temperature. Okay? If the line was curved, it would mean that that object is not at a constant temperature. This is Ohm's law. So as I increase the voltage, the current also increases in direct proportion. Okay? That's not what happens in a light bulb. In a light bulb, it's not directly resistant because a light bulb actually changes its temperature. It gets warmer when it gives out light. So if you were to look at the resistance of a light bulb, it actually looks more like this. It's sort of flattened off, then goes up and then flattens off again. Okay, it does not follow Ohm's law. It changes its resistance dependent on the temperature. It's not a constant temperature. If you, so if the line is straight, that means the object is at constant temperature. If the line is steeper, that means the resistance is actually lower. More current is flowing for less voltage. So a steeper line actually means that the resistance has actually changed, okay, on the object. So that's how you can tell, like, the resistance of the line based on that. Okay, sorry, the resistance of the object. Okay, by the steepness, the gradient of the line. In a series circuit, okay, in a series circuit, which is one type of circuit, we are talking about one loop. So a series circuit is a circuit that all the components are on one loop around. So we've got one loop in the circuit. It's made up of a cell, a switch, which at this moment is open, but we can close it to allow electricity to flow and the bulbs will light up. There are two bulbs in this circuit. It is a series circuit because there is only one loop around. Okay? Now, with a series circuit, if there is a break anywhere in that circuit, so if one of the bulbs blows, electricity will not be able to flow around and both bulbs will go out. Okay? So that's the first thing about it. In a series circuit, if there is a break anywhere in the circuit, electricity will stop flowing. Okay? So that's important. And then in a series circuit, we can follow a few rules to find out a few facts about it. And they often ask you questions about similar to this. So I'm going to draw up that circuit, but I'm going to say that the switch is closed at this point and electricity is flowing. If I was to measure the current at any point in this circuit, well, actually, first I'll take a step back. I should say, how would I measure the current? I've got to add an ammeter into the circuit. Now, if I wanted to measure the current of this circuit, an ammeter is always put in series. So you can just place it anywhere on the loop. It doesn't matter where in a series circuit, but I could place an ammeter on the loop is what I would do to measure the current. Okay? And they sometimes ask you where, or draw on this diagram, where you would add an ammeter to measure the current of the circuit. If I was to measure the current at this point, and I found the current to be 0.5 amps. Okay? If I found the current at that point to be 0.5 amps, if I was to measure the current here in between the bulbs, it would also be 0.5 amps. Okay? If I measured the current here. So if I put an ammeter in here, the current would also be 0.5 amps. And if I was to measure the current over here, guess what it would be? 0.5 amps. The current in a series circuit is the same anywhere in the circuit. All the way around, the current in a series circuit, it remains the same. Okay? So that's the first rule about series circuits. The second rule is the potential difference that this cell or battery is supplying is shared between the components that are in that circuit. Now if these were identical bulbs or identical resistors, they would have exactly the same voltage going to each. So I haven't drawn it out very well, but if I was to say this battery, I've just drawn a cell, but if I was to say this battery was supplying 6 volts of electricity, I'm going to keep the numbers simple, then if I was to measure the voltage that was supplied to this bulb, I would find that that would be exactly, if they were identical bulbs, half the amount that was supplied to the entire circuit. And to measure the voltage, this is another thing they occasionally ask, where would I put my voltmeter? Well, I would put my voltmeter across the component I was trying to measure. So I put it like that across that bulb there. And when I measured the voltage, I would see if these were identical bulbs, the same bulb, 3 volts. And this bulb would also have 3 volts. Okay. The amount of electricity, or the amount of potential difference, the voltage, between these two bulbs is exactly shared by half. Okay. So if I was supplying 6 volts via that battery, each bulb would be getting 3. Okay. Because they're sharing the energy, both bulbs would be quite dim because they're sharing the energy. They're only receiving half the amount I'm supplying each. So both bulbs would be lit up, but they would both be dim. And if one of the bulbs was to blow, this bulb would go out. It would stop working because I've broken the circuit, the electricity wouldn't be able to flow to this point. Okay? So that's a series circuit. The current is the same all the way round, and the voltage is shared between the components. Okay? If they're identical, it's shared exactly. If they're non-identical, they'd have to give you some information to work out exactly what each was getting. Okay? Also, with a series circuit, the last thing you could do with it, if I was to know the resistance of these two bulbs, I could work out the total resistance of the circuit. Okay? If the resistance of these bulbs was, let's just keep it simple again, 10 ohms. Okay. To work out the total resistance of that circuit, in series the total resistance is just equal to the resistance 1 plus the resistance 2. Or if I had 3 components, it would just be adding all 3 together. So in this case, it would be 10 plus 10. My total resistance is equal to 20 ohms. Okay? That would be for this series circuit. Okay? So current is the same all the way around, no matter where you measure it. The potential difference is shared between the components. If they're equal or identical components, it's shared equally between them. And to work out the resistance, you just add up the resistance of all the components that are in that circuit. Okay, that's the series circuits. And what we're actually going to move on to is looking at parallel circuits. Now what a parallel circuit is a circuit which has more than one loop in it. So it has more than one loop. Shown over here. So we've got one loop that goes round there, and another loop that goes round there. Okay. With that, the electricity is flowing around both loops at any one time, and if I was to break the circuit here, it could still actually go through here and light up this bulb. Okay. If I was to break it here, it could still flow through and light up this bulb as long as this switch was closed. So if I was to draw out that circuit, I'm going to ignore the switch this time because it's irrelevant to what I'm trying to do here. Let's just assume it doesn't have one. If I wanted to measure the current flowing in that circuit, I'd put my ammeter in series, but there'd be different places I could do it. I could do it here, I could do it here, I could do it here next to this bulb, and I could do it here next to this bulb. This would actually make a difference in this case. Okay? Now I'm going to assume they're identical bulbs again. So if they're identical bulbs, this works perfectly, but if they're not, they would have to give you some more information, but you can still work out different bits. If I measured the current here, and this was 0.5 amps, and then I measured the current at this point, and it was 0.25 amps, the current here would be 0.25 amps. It is shared, because these are identical bulbs, equally between the two branches. Yeah? When these, that's because electricity flows through here, all the electrons flow past this ammeter, and then half go this way, and half go that way, and then they join back together at this point. So 0.5 amps actually comes and flows back round to the battery. Okay? So if they're identical bulbs, the current is split equally between the two branches. If they were non-identical bulbs, if I was to just do a quick example of that, or one was a resistor maybe that was different. If I was to be given the two currents here, so ammeter, ammeter, and I found the current here to be 0.4 amps, and I knew the current going into them was still 0.5 amps, I could actually work out this missing current that must be going through this resistor by doing 0.4 subtracted from 0.5 to give me 0.1. These two together must equal what goes in. And when it comes back, it would be back to 0.5 returned to the battery. Okay? Now voltage is slightly different, or potential difference is different. Potential difference across each branch of a parallel circuit is the same. So if this was 6 volts, okay, now again I'm going to say, I haven't drawn this very well, like each cell usually is 1.5 volts, that's what we consider a cell to be. But I'm drawing this just one cell to be 6 volts, so I'm cutting a few corners, but if 6 volts are supplied to this circuit, then each of the components in the branches gets 6 volts. Okay? So this receives 6 volts and this receives 6 volts. Similarly, it doesn't matter if they're different, these are the same bulbs, remember, but if this was to supply 6 volts, this bulb would be getting 6 volts and the resistor would be getting 6 volts. Okay? Everything in a parallel circuit, every branch gets the same potential difference. Okay? If I was to measure the voltage. Remember, my voltmeter must go across the component that I'm measuring if I was to draw it in. But each component, each branch in a parallel circuit receives the same voltage. With that, I could actually work out the resistance of this resistor because I could use, if I go back to my formula, V equals IR. If I wanted the resistance, I know the voltage, 6 volts, because it's the same as the cell. I know the current, 0.1. I would have to work out the resistance. It's actually V divided by I, which is the voltage divided by the current. It would be 6 divided by 0.1 to mean this resistor is actually 60 ohms resistance. Okay. One last quick one I'll just show you is if you've got a sort of series and parallel circuit, it can come up very occasionally. If I had a circuit like this, where I had 2 bulbs there, and I had one there. Okay. If I was supplied a potential difference of 6 volts, if all the bulbs were identical, each branch gets 6 volts, so this would receive 6 volts because it's the only bulb on that branch, but these, because they're in series with each other, would get half of that 6 each. Very unlikely to come up, but if it did, you could see how you could work out the potential difference across several bulbs in series, but in parallel as well. Okay? So that's series and parallel circuits, okay, and going on to it. The sort of things they want you to know about it. That's if we've got a battery. Now batteries supply direct current. Direct current, definition, is current that only flows in one direction around the circuit. Battery supplies direct current, it's only going round in one direction, okay, flowing around. Electricity that we get from the sockets is actually called alternating current, AC. Direct current DC, alternating current AC. That means it actually flows around the circuit one way and then flicks and flows the other. And it keeps doing that a number of times a second. It actually flicks, it's so fast that it's going one way and then the other number of times every second. Okay? In fact, for mains electricity you need to know it's 50 Hertz, which means 50 cycles per second. Every second it's flicked backwards and forwards 50 times. Okay? So alternating current is current that flows one way and then the other. Direct current, it only flows around one direction around the circuit. Okay? That's the difference. And mains electricity in the UK is alternating current, AC. You also need to remember these numbers, unfortunately it's the only way to do it, that the voltage is 230 volts and the frequency is 50 Hertz, which as I said means it flicks backwards and forwards 50 times every second. Okay. If we were to look at alternating current on what's called an oscilloscope, you can see the pattern of it, and it would look like this. It's flicking one way, positive, then negative, a number of times every second. The voltage is actually determined by the height of the peak from the midpoint. So if I knew each of these squares was 1 volt, this is 3 squares high, so it's actually 3 volts is the voltage of that current. And then also I could work out the frequency of it. The frequency, if I know how many these squares are, or what time period they are, you would be told these are each 0.1 of a second. This actually covers 4 squares, so it's 0.4 seconds for one wave, for one down, then up, or up, then down, doesn't matter. It's still 4 squares for one wave. So if I knew each of the squares was 0.4 seconds, that would be, 0.1 second, that would be 0.4 in total, and to work out the frequency, it would be 1 divided by 0.4, which would actually tell me the frequency in Hertz. Okay. Again, that's a thing that is unlikely to come up, those sort of things on alternating current, but it's worth just remembering, and if you've got the PowerPoint, you've got it there to see that. That calculation, that formula is not actually given to you, it's one of the ones that you may have to remember. Plugs, okay, these come up fairly regularly. You need to know how to wire a plug, you need to know what the different wires do and what the different materials are made from. The wires themselves inside these cables are actually made of copper, and the reason being is copper is bendy, so the wires can bend, but it conducts electricity, so copper is used for the wires. The plug itself is actually made from plastic. The reason being is plastic does not conduct electricity. You don't want to touch a plug and get electrocuted, so it doesn't conduct electricity, but it's also strong, so it keeps its shape. And you can't see on this picture the pins that come out the other side of the plug. So if you look at a plug, it's got 3 pins that come out of it. And the pins are made of brass, which is an alloy of copper. Brass because it conducts electricity, but it's not flexible, it's strong, because you don't want the pins that go into the plug socket to bend, and therefore you wouldn't be able to fit your plug into the socket anymore. So the wires are made of copper, conducts electricity, and are flexible so it bends. The pins are made of brass, conducts electricity but does not bend, is strong, so they don't bend when you put them into the socket and therefore break. And the plug itself is made of plastic, which doesn't conduct electricity but is hard, is tough, keeps its shape. When wiring a plug, you need to know what the different wires do. So you have a blue wire, a brown wire, and a yellow and green striped wire. The first wire goes to the pin at the top, the yellow and green striped wire. It's called the earth wire. The way I remember it's the earth wire is the yellow and green striped wire, is that green is the colour of the ground around us, or the earth. The earth is green, okay, because we have plants or grass on it. So I remember the earth wire is green because we're a green planet, okay? We like to be green. So that's how I remember the green and yellow one is the earth wire, and that goes to the pin at the top. Then you've got the neutral wire, which is the blue wire, is neutral. And the way I remember that is water is blue and water is also neutral. Okay, so water is neutral, the neutral wire is blue. That goes to the pin without the fuse on it, the pin that is not attached to the fuse. The pin that is over on the left hand side, if you're looking at a plug this way, and not attached to anything. Okay, so we've got our earth wire is green because the earth is green. The neutral wire is blue because water is neutral. And last of all, we've got the live wire. The live wire is the brown wire. And the way I remember that is because the live wire, if you touch it, that's the one that's likely to kill you. And unfortunately, do you know what happens if you die from touching a live wire, or die anyway? You lose your bowels, okay? You poo yourself, not to put too fine a point on it. So that's brown, okay? That's how I remember it. I know it's silly, but it's a way of remembering. And at this stage, I don't care if you remember it anyway for your exam. So brown is the live wire, because if you touch it, you're going to die, and if you die, you'll poo yourself, okay? Good way to remember. It's also the one that's always attached to the fuse, okay? It's attached to the fuse. Okay, and that's important because the fuse is a safety feature, okay? We'll come to that in a second. I'll just talk about the earth wire. The earth wire is attached to an object if it has a metal casing. I mean, all plugs in the UK have an earth wire, and that's actually connected to the ground. It's because if an object which has a metal case has a fault, the metal case is a good conductor and could become electrified. If you were to touch it, it could electrocute you and possibly kill you. So the earth wire actually connects that metal case to the ground because electricity wants to get to the ground. Now if you touch it, the electricity is more than happy to go through your body into the ground, and in which case you will get an electric shock and potentially die. The earth wire is a quicker route for it to get to the ground. So if the appliance is faulty and the metal casing is electrified, when you touch it, the earth wire recognises that fault and sends the electric current to the ground and not through you, so you're safe. Okay, so that's what the earth wire is. It's a safety feature to prevent the metal casing of an appliance becoming electrified. The fuse is another safety feature in a plug. What the fuse is, it's actually contains a thin wire which is made of a metal with a low melting point, meaning it will melt very easily. If the current becomes too large in the live wire, and there's a risk, a danger again of electrocution, that wire inside a glass tube actually melts. And when it melts, it will break, and that stops the electricity flowing because the circuit is broken. With fuses, what you need to know is there are three types of fuse you can use. There's a 3 amp fuse, a 5 amp fuse, and a 13 amp fuse. I believe it's 13 amp. I will check, just confirm, but a 13 amp fuse. And what you need to remember is you will be told the different fuses you can use in an exam question anyway. And what you need to remember is the fuse that you are using for an electrical appliance needs to be greater than the current flowing through that electrical appliance. But you still use the lowest fuse that is possible to use. So if I had an appliance which had a current of 2.5 amps, I could use a 3 amp fuse because that's bigger than the 2.5. I could technically use the 5 amp fuse as well, but that would not be a good idea because it's much higher than the current that it needs to flow, and in which case would not maybe cut off if the current got too large and there was a risk of danger. So you always attempt to use a fuse that has the current just above the current that you are measuring, but not as close as to it you can get. Another example could be if I had an appliance that had a current of 4.5 amps, I would use the 5 amp fuse because it's above the current I need to sustain, but I could not use the 3 amp fuse because it would be too low and it would melt even when the appliance was working perfectly. I wouldn't go up to the 13 amp fuse because that would be too large a jump, and if that appliance had a fault it would not melt and cut off. In UK homes we tend to have also what's called a circuit breaker, sometimes shortened to a RCCB, a remote controlled circuit breaker. That's the box you might have at home that if something happens, something goes wrong at home, it's actually an electromagnet that causes a switch to cut off and electricity supply to be cut, again to prevent you from harm. Okay? The good things about those is they act faster than a fuse because you don't have to wait for the wire to melt, it just instantly cuts the electricity. And with a circuit breaker, you can actually just flick it back on once you've worked out what the fault is and repaired it. Whereas with a fuse, the wire in it actually melts, so if it melts you have to replace the entire fuse. Okay? So fuses are circuit breakers, safety features of appliances and earth wires that you need to know a bit about. While we're talking about electrical circuits, I'm just going to give you two equations for calculating power. Now, power is measured in watts. A common science joke is to say watt is the unit of power, because it is the unit of power. Okay? So power is measured in watts. There are two equations for calculating the power. One is power is equal to the energy transferred divided by time. It's on your handy formula sheet, you will have it. And the other one, often used in electrical appliances and electrical circuits, is power is equal to the current multiplied by the voltage. Okay? So these are two ways of working out power, and you can be asked to work out the power of an electrical appliance. Similarly, you also need to work out energy and work done. Now, energy is equal to work done. It's when an object is moved by a force, we say work is being done and energy is being transferred. They are the same thing. Energy is always measured in joules. So the units for energy are always joules. If you're working at an energy, the units are going to be joules. And you can calculate the amount of work done. Again, it's on your formula sheet by doing a simple formula, the force applied multiplied by the distance the object moves. Okay? That's how you calculate the amount of work done. So that means if I was to move this board and I had to apply a force of 10 newtons and I moved it 1 metre, okay, that would be the distance, okay, I would do 10 newtons multiplied by 1 metre, 10 times 1, I had to use 10 joules of energy to move that board. Okay? So you can calculate the work done to move an object by doing the force that's applied to that object, and that's the result, or could be the resultant force that you've worked out earlier, multiplied by the distance that object moved. Okay? You also need to do calculations. I'll go through these quite quickly. They are on the formula sheet for gravitational potential energy. Now, the gravitational potential energy is the amount of energy stored in an object relative to its position on the Earth, so due to gravity. This pen that I'm holding here has gravitational potential energy. The energy can be released if I release the pen. It causes it to move down. Okay? So any object that's off the surface of the Earth has gravitational potential energy, has the ability to fall. And you can calculate it by doing the mass of the object multiplied by the gravity, which I said on Earth is 10, always 10, but you will be given it, multiplied by the height of the object. So if this object was 1 kilogram and I had it 1 metre off the ground, gravity on Earth is 10, so 1 is the mass, 1 kilogram, multiplied by the gravity 10, multiplied by the height of 1 metre, it means 1 times 10 times 1 is just 10. That would have 10 joules, because gravitational potential energy is still an energy, stored in it. Now when I released that pen, it fell. And some of you might be able to tell me that it's converting the energy into, or transferring the energy into kinetic energy, which is movement energy. It's the amount of energy stored in an object relative to its mass and its speed, an object that's moving. You can again calculate this by doing an equation which appears on the equation sheet. It's one of the tougher calculations you have to do actually. It's equal to 1/2 times the mass times the velocity squared. So you will need to be given these things. Okay? A thing they like to do is, if you've worked out the gravitational potential energy of an object that's up in the air, when I drop it, it converts the energy into kinetic energy. Just before that object hits the ground, it should have converted all of the gravitational energy into kinetic. So if I worked out the gravitational potential energy of that object when it was off the ground, so I said this had 10 joules of energy, the amount of kinetic energy just before it hits the ground is equal to 10, the same. It's transferred all of its energy to kinetic. Then if I know its mass, well, its mass won't have changed, it will still be 1 kilogram, okay, just because it's fallen through the air, its mass isn't going to change. And then I'll be able to work out its speed by rearranging this formula, which is one of the tougher things to do, because you actually have to multiply it by 2 to get rid of the half, divide it by the mass, and do the square root to find the velocity. That's a more tricky thing to do, kinetic energy or conversion. Now they like to ask questions about kinetic energy and fairground rides, such as roller coasters. Only briefly going over it, is because the amount of gravitational potential energy stored in this roller coaster up here will be equal to the amount of kinetic energy it's got when it's at its lowest point. And then it can convert it back to gravitational potential energy when it moves back up the slope. Okay? The amount of energy it's got here will never be the same as the amount of kinetic energy it's got here, because there is always some energy lost. And if they ask you about that, the energy is lost as heat due to friction, which is it rubbing past the railings or the wheels rubbing on the track. Okay? So energy is always lost in an energy transfer from gravitational potential energy to kinetic as heat due to friction. Okay? So that's the energy transfer that's going on. Momentum. We're going to talk briefly about momentum because I want to get onto radiation, and we only have a little bit of time actually left. So I'm going to go briefly over momentum and then we'll do radiation just at the end. Okay? The momentum of an object is the tendency of an object to keep moving. Okay? So if you're running, okay, and something tries to stop you, your momentum will oppose that force trying to stop you, or want to keep you moving in the same direction. It depends on two things. It depends on the mass of that object and how fast that object's moving, its velocity. The equation, again, is found on the equation sheet. You will have it, so you will be able to find it. It's actually momentum is mass multiplied by the velocity. The funny thing with this equation is, though, that momentum is given the symbol P. Okay? Mass is m, so they can't use m for momentum, so they use P. P is equal to mv, mass times velocity. That's easy enough to calculate. So you can calculate the momentum of an object just by multiplying its mass by its velocity. But when you're in a closed system, so a system that doesn't have things changing, if two things collide, momentum must be conserved. It must be the same before as it was afterwards. Okay? And often if they say, what does the conservation of momentum mean? It means momentum before must equal momentum after, or momentum at the start must equal momentum at the end. And they use that as an example in explosion. So when the explosion happens, or whenever two objects push away from each other, momentum is conserved. They often use a skateboarder as an example. It means if two objects push against each other, so in this example, the boy jumps off the skateboard, the boy will move in this direction, and the skateboard will move in the opposite direction. Okay? Because momentum must be conserved. The momentum at the start must equal the momentum at the end. Because they're moving in equal and opposite directions, at the start, when they're stationary, I should have probably started with this, but an object which is stationary has no momentum. Its momentum is zero. If I'm stationary, my momentum is always going to be zero. If I start to move, okay, then if I've pushed off of something, the momentum must be conserved. So momentum must be equal in both directions. If I push off an object that can move, like a skateboard, because the momentum is equal, I can actually work out what the mass and velocity of both objects is. Now this is a higher level skill, but momentum to the left must equal momentum to the right. So you can do that by doing momentum, which is mass times velocity of one object, is equal to the mass times the velocity of the other object. Okay? So if ever you get a question where they give you three numbers, the mass and velocity of one object, and then possibly just the mass or possibly the velocity of the other object, the first thing you need to write is m times v equals m times v. Write the mass of one of the objects and write the velocity of that object in the equation, and then write the mass or the velocity of the other object, the other side of the equal sign. For this one, you probably can't see it on the screen, but I'll tell you, it says the mass of the skateboard is 1.8 kilograms. So I'll put 1.8 kilograms multiplied by the velocity of the skateboard, but I don't know what that is yet. The mass of the skateboarder is 42 kilograms. So his mass is 42 kilograms. Then, calculate the velocity of the skateboard moving backwards. Well, this is the skateboard, this side, so I'm going to leave that as v, the velocity of the skateboard, if the skateboarder moves forward at a velocity of 0.3 meters per second. Okay, so 0.3 is his velocity. Once I've put those numbers in, it's just a simple case of rearranging the equation or doing the sums. I'm going to do the sum on the left-hand side first. So 42 multiplied by 0.3 tells me this is 12.6. Okay, that's the momentum of the skateboarder. Now, because momentum is conserved, the momentum before must equal the momentum after, the momentum of the skateboard must be the same. That's still 1.8 times v. If I wanted to take this 1.8 over to this side to get v, I would have to divide. So v is equal to 12.6 divided by 1.8. 12.6 divided by 1.8 is actually 7 meters per second. So that's how I can calculate the velocity of an unknown object in after a collision or after momentum's been conserved. So I said I'd go on to the last thing, which is to do with radiation, and discovery of the atom comes into this as well. So we'll look at the different types of radiation, discovery of the atom, and finish with a little bit about fusion and fission, two types of ways of generating energy using a nuclear reaction. The discovery of the atomic structure. Now, in about the 1900s, they said that the atom, sorry, I'm standing in the way, was a big ball of positive, like a positive particle, with tiny little negative particles scattered through it. Okay, or areas of negativity or negative. The positive bit they called like a plum. The pudding, and the little negative bits were the plums in the plum pudding. A plum pudding is probably a bit of an old analogy for some of you watching this. It's like, I think of like a Christmas pudding, and the negative bits are like the raisins spread out through the pudding themselves, which is the positive bit. Okay, so the pudding is actually a big lump of positive with these negative little pieces in it. So that's what they thought an atom was like. Now, in about 1905, Ernest Rutherford came up with an experiment to test whether this was true. He actually fired what's called alpha particles, which are a type of radiation we're going to look at this very thin sheet of gold foil made up of just one atom of gold thick. And what they were expecting is they were expecting the alpha particles to pass straight through, the radiation to pass straight through. And some of it did. But some of it actually hit something and was deflected or bounced off. And that led them to believe that it wasn't just one solid positive lump with negative bits scattered through it. It actually was mainly nothing, which the radiation just passed through, or empty space, with a very, very tiny positive centre to it. And they actually changed the model of the atom to the atom that we know now, where it's got the positive nucleus in the centre, which is what the alpha particles were hitting and deflecting off, and the electrons in shells, which the alpha particles just passed through because there was nothing really in the way. So they actually changed the idea of what the model of the atom was, from this plum pudding model with a big lump of positive with little areas of negative particles floating through it or in it. And they changed it to this model with a tiny dense ball of positive charge in the centre with empty space around it through which the alpha particles could pass. So I said we'd look at like alpha particles and the different types of radiation that can be given off by a substance. The first one to look at is alpha. Alpha is a type of radiation that can be given off by a substance. It's actually where you've got a nucleus, a very large nucleus, that's the centre of an atom, and it actually releases 2 protons and 2 neutrons, which is the same as a helium nucleus. It actually releases. It has a mass of 4, because protons and neutrons you add together, and an atomic number of 2, which is the same as a helium nucleus. When it decays and releases an alpha particle, it actually releases this, and this is your alpha particle, breaks down to make a new element. And you can work out what new element because it loses 2 protons, the atomic number goes down by 2, and the mass number goes down by 4. And you can look in the periodic table to find out what that new element formed would be. That's alpha decay. Now alpha particles are quite big, 2 protons and 2 neutrons, which is relatively large. They are the most damaging type of radiation. If they hit you, they will damage you. But fortunately, they don't travel very far through the air. Their range in air is very small, a few centimetres. They also are blocked by a thin sheet of paper, so they can be blocked by paper. They're not very, we say it's their penetrating power, they're not very penetrating. Okay, they're blocked by paper. I will summarise all this in a second. The second type of decay we can get is called beta decay, and is given this symbol here. Okay? Beta decay is when a neutron actually changes into a proton. And when it does that, it releases a high-speed electron, flies out of it. Okay? This is the beta particle. It's actually given this symbol. The mass number doesn't change, but the actual proton number drops by 1 because of that change that's going on. So the proton number, actually increases by 1 because a neutron turns into a proton. They both have the same mass, so that's why the mass doesn't change. So 14 to 14, because it's not going to change the mass, but because the neutron actually turns into a proton, the proton number goes up by 1. Okay? The reason this is negative over here, because if you do that sum, 7 minus 1, it actually equals 6. So that's why a beta particle is given this symbol here. You don't actually have to write that out. You could just put a beta particle unless they specifically want it. And these equations for radioactive decay don't come up very often, I have to say. If they do, you would know the atomic number goes up by 1 to 7, and you could look in a periodic table to find the element is actually nitrogen that's produced from beta decay. And the third type of radiation that can be given out is actually gamma radiation. Gamma radiation is just energy that's released in the form of a wave by a nucleus. It usually follows alpha or beta decay. So once a nucleus has decayed and released alpha or beta radiation, it sometimes also releases gamma radiation. It doesn't have any mass or any charge. Okay, so it travels a long distance through the air. I didn't actually mention that beta has a distance of about a metre or a metre or so through the air. And in terms of its penetrating power, it can pass through paper, so it could get through a sheet of paper beta radiation, but it's stopped by a thin layer of aluminium. Now, gamma can pass through paper easily, and it also passes through aluminium. The only thing we use to stop gamma radiation is thick lead. It can be stopped by a thick lead sheet, or several metres of concrete can stop it as well. But its penetrating power is high. Its ionising power, though, that's how damaging it is to us if it hits us, is fairly low. It's quite weak. It doesn't really damage us if it hits us. That's not to say you would like to be exposed to lots of gamma radiation. It can still harm us, and what it does is it damages our DNA and can lead to cancer by causing mutations in the DNA. But it's not as damaging as alpha. Okay, alpha is big, and beta is in the middle. Generally, beta is in the middle. This table you probably won't be able to see on the board now, but if you've downloaded the slides you can see it. It tells you all of the information about alpha, beta and gamma. So I highly recommend you look at it and look it up. It tells you their range in air, gamma being unlimited, can travel forever. It tells you what they can be stopped by, their penetrating power. It tells you whether they are deflected by electric fields, which I haven't talked about. It also talks about their charge and their ionising power as well. Okay? Because alpha particle is 2 protons and 2 neutrons, the neutrons have no charge, but the protons are positive, so it has a charge of +2. Beta particles, because they're fast-moving electrons, electrons have a charge of -1. But as I say, that table is definitely something I'd suggest you look at and get the information from. Half-life, just to do with radiation, the half-life of a radioactive material is the time it takes for it to decay by exactly half. If you plot a graph of it, it will always look like this, okay, a curve that goes down like that. And there's 2 ways you can actually use it. Okay? From the graph, you can work out the half-life of this material. Okay? When I say half-life, radioactive decay is random. It takes place at random, which is very important. And actually, there are levels of background radiation you're exposed to all the time. So we're being exposed to radiation, which is called background radiation. We can measure background radiation, and you can measure radiation using a Geiger-Müller tube, but you will always pick up some radiation. Most of that radiation is called cosmic radiation. We learned about cosmic microwave background radiation when we did P1, and that will affect your reading on your Geiger tube. It's always going to pick up some radiation because of cosmic radiation. Some of it comes from medical sources such as gamma used to treat cancer or maybe X-rays, and then some of it comes from food. Most radiation though actually comes from the air around us. There's a gas in the air called radon, and it actually releases most of the radiation we're exposed to. But it's not harmful background radiation. We're exposed to it at all times, and our body is designed to cope with it. Only if the levels are higher than that will we actually be damaged by it. So radioactive decay happens at random. You can't predict when it happens. But what we can do is we can actually see a pattern in radioactive decay. And we call that the half-life. It's the length of time for a material to decay by half. In this example, there's 80. That's 80 counts. So 80 decays per minute are happening at this point. A half-life, to get the half-life, what we have to do is we have to work out that if it starts at 80, what's half of 80? It'd be the time it takes to decay by half, so it goes down to 40. Okay, half of 80 is 40. And we go along and we look down. The time at the bottom here is in days, and that takes 2 days for it to decay from 80 to 40. Okay? 2 days. That would get you 2 out of 3 marks in an exam if you were asked to find the half-life from a graph. To get the final mark, you need to check it at least once. And to do that, you use the graph again. If I was to do another half-life, what would it go down to? It wouldn't go down to 0, because it went down by 40 the first time, does not mean it will go down another 40 to 0. It means it will go down by half, because this is a half-life. So from 40, if it was to decay by half, it would go down to 20. If I go to 20 and across, I'm now at 4 days. So it's increased by another 2 days. 2 days has gone by for it to go down by half. And do you know what? If I really wanted to be certain, I could check a third time. Half of 20 is 10. If I go along to 10 and down, I'm now at 6 days. Another 2 days has passed for it to go down by half. So my half-life for this material, whatever it is 2 days. It takes 2 days for it to decay by half. Okay? Decay is random. You can't predict which nucleus or nuclei are going to decay and release radiation, but over time, in 2 days, half of them approximately would have decayed, and after another 2 days, another half would have decayed. You can use that to work out the age of a substance. Now, the age of a substance can be worked out. If we had an exam question that said a material contained 160 grams of a radioactive material, and after several half-lives, or after a period of time, let's say after 15 years, 20 grams remained. Okay. We could work out what half-life was from that information without the graph. The way we would do it, the way I would do it, is draw out how many half-lives have occurred. So for this, started at 160. If it was to go down by one half-life, there would be 80 left, because that's half of 160. And then another, it would be how many which would be down by? It would be down to 40. Half of 80 is 40. And after another half-life, I would be at 20. So 20 grams. Okay, 20 grams remain. How many half-lives have gone by? Well, that's how many arrows there are. Not how many numbers are here, but how many arrows. Each of these is a half-life, and the symbol for half-life is T, a half. So 3 half-lives have passed. If after 15 years I would know it would be 3 half-lives, I could do 15 divided by 3 equals 5 years. Each half-life is 5 years. Similarly, I could have done it another way. If I was told the half-life was 5 years, and I did this, and I worked out that 3 half-lives had gone by, and I knew each half-life was 5 years, sorry, I could do my 5 multiplied by my 3 half-lives to know that it would take 15 years for 160 grams to decay to just 20. Okay? So that's how you can use half-life. You can do it from a graph by reading off the graph when half the count has dropped. 2 days, half again would be 20. That's another 2 days. Half again would be 10. Another 2 days. So I know my half-life is 2 days. Or I could do it from some information. Write out the number of drops it takes. 160 would go to 80, 80 would go to 40, 40 would go to 20. It falls by half each time. There is half the amount of material left. A use of this is carbon dated. So they use this to date old objects. So carbon dated is used to date an object that was alive at one point, such as a living organism or a plant, or a fossil that you had. You could carbon date it by finding out the amount of carbon-14 that was left in it. So you could find the amount of carbon-14 that was left in that material, work out how much carbon-14 there should be by knowing the mass of that material, and then you could work out how many half-lives have passed, and then work out the age of that object. It's called carbon dating, by using the half-life of carbon-14 to work out how old the object is. If you're working out the half-life or the age of a rock, they actually use uranium in the rock, but they do the same thing, work out how many half-lives have passed for that object, for that rock, and then work out the age of it. Okay. Right, so the very last thing, I know I've gone over a bit, but I want to round this off to the last thing to go over, nuclear fission and nuclear fusion. Okay. So very quickly, nuclear fission is a process used to supply energy in nuclear power stations. Okay? Our nuclear fission power station uses enriched uranium-235 or plutonium-239 as the fuel, and you need to know the fuel that's used. It is a chain reaction, nuclear fission, and it results in lots of energy released. Okay? What happens is one neutron is fired into a nucleus of uranium or plutonium. That nucleus actually splits into 2 new nuclei. And that's what fission is, the splitting of a nucleus. Nuclear fission, to split a nucleus. Fission is to split. And when it splits, it will release neutrons. Those neutrons could go on and hit more nuclei. They could hit 3 more if 3 neutrons were released. And they would split and release 3 neutrons. So that would give us 9, and that would hit 3 more and go up to 27. Okay? And this is a chain reaction because it carries on. And each time this nucleus breaks up, it releases energy. So one neutron is fired into a nucleus, which makes it unstable. It splits in half and releases neutrons, which go on to hit other nuclei. Hence, it's a chain reaction. Now, in a power station, they don't want this getting out of control. So in a nuclear power station, they actually use what's called control rods made of boron to absorb some of the neutrons that are released. And if they absorbed all of them, they could stop the reaction. If they absorbed some of them, they could just slow it down. Okay? So they can use the control rods which are lowered into the reactor or raised out of the reactor to control the speed of the reaction, to stop it getting carried away. If you're asked to describe a nuclear fission or chain reaction, you can use this diagram to show what's going on. Okay? One neutron is fired into a nucleus which splits in half and releases 3 neutrons, which can go on to hit other nuclei, and they split and release neutrons. Okay? So that's nuclear fission, splitting of a nucleus. The other way that scientists are trying to develop to release energy is nuclear fusion. This occurs naturally in stars like our sun. It's happening. It requires a very high temperature and pressure. In fact, our sun is about 15 million degrees Celsius in its core. Scientists have not been able to recreate this extreme condition on Earth yet, but they are trying. Well, they haven't been able to on a large scale, maybe on a very small scale. This releases loads of energy, and fusion means actually nuclei coming together to make a new nucleus. The 2 nuclei that come together, fuse together, join together, are deuterium, which is obtained from water, which is readily available, and tritium, which is found in lithium or made from lithium. These 2 nuclei are forced together and they fuse, they join to create a helium nucleus, and they release 1 neutron. But they also release loads of energy in the process. Okay? This is the process that is happening in stars that actually forms new elements. This fusion of elements together, or nuclei together, forms new elements. A common question, and can be the 6th marker, is to compare fusion and fission. Fission, the advantages is we already have the power stations ready. There are no greenhouse gases released. But its disadvantages are, it does create nuclear waste, which we have to dispose of. Currently, we encase it in concrete, put it in a steel drum, and then bury it underground or drop it in the ocean. There is a chance of a meltdown. Because it's a chain reaction, it can go out of control if it's not controlled by the control rods, or if the control rods fail. So there's a chance of a meltdown, which would mean a nuclear disaster. And the fuel, uranium or plutonium, can also be used to create nuclear weapons, which is not good. Fission, on the other hand, has lots of advantages. It doesn't release much radiation, so it's not as dangerous as this is fusion, as fission. The fuel is abundant. There's loads of it. I said we get deuterium from water. Again, no greenhouse gases are released, but lots of energy are released. And it doesn't really produce radioactive waste that has to be disposed of. Okay? The big disadvantage with fusion, though, is that scientists have not carried it out on a large enough scale for us to actually use it effectively. But they are attempting to develop this process now because it would provide us a near unlimited supply of energy to power the future, if we could do it. So you need to be able to make a comparison between fission and fusion. Now you need to know fission is a chain reaction and what is actually going on in the process. And fusion is forcing the nuclei together to build a new nuclei, and it releases lots of energy in that process. I have gone over, I apologise for that. The last thing I'll leave you up just on the board, just briefly, is the life cycle of a star. Okay, I'm not going to go into it because, as I say, I've run over already, but if you look at my PowerPoint, you have this. This is a question that comes up. The main bit you need to know is the fact that there are 2 routes it can take, depending on the size of the star. If it's a normal sized star, like our sun, it becomes a red giant and then goes on to white dwarf, black dwarf. Whereas if it's a larger star than our sun, it actually goes on to form a red supergiant and then can explode in a supernova and become a neutron star or lead to a black hole. Okay? So the different size stars have different life cycles. Okay? They all start as a protostar in a nebula, but they can go different routes after that point. Our star, they believe, is a second generation star because we contain heavy elements which are not generated from normal nuclear fusion. Normal nuclear fusion only creates elements up to a mass of iron, but our planet has heavier elements such as uranium, which they believe are formed in a supernova explosion to create those elements. Okay. So as I say, I did go over by a fair amount, by about 15 minutes. So you've got more bang for your buck out of me today. I'm pretty knackered now. I hope it's been worthwhile for you. And like I say, you've got it tomorrow to watch during your lessons or at home. Do download the PowerPoints if you can and use those slides to get the most out of this. And all that's left for me really to say is just thanks for watching all these videos and all the effort you've put in so far. I know all the team here at the Folkestone Academy have been so impressed with your effort and how you're doing and how you've approached the exams with positivity. And just the last thing I always say is just good luck on Friday.